Good morning, students. So in the last class we discussed design of counters using Jacob flip-flop, and in today's class we will see the design of counters using SR flip-flop. So first we will design mod 4 counter, using SR flip-flop, right? So first we need to write the truth table of SR. S and R outputs are Q and Q bar. S and R are 0. Since there are two inputs S and R, we need to write 4 combinations. We can write 4 combinations: 0 0 0 1 1 0 and 1 1. And according to the truth table of SR, when S and R are 0, the first state is going to remain same. That is no change in the first state or previous state, you can say. When S is 0 and R is 1, the flip-flop is going to reset. When S is 1, flip-flop is going to set. And when S and both are 0 0, then we will be having a forbidden state as per the basics of SR flip-flop. We call that state as forbidden state because the Q and Q bar are not complement to each other. With this truth table, we are going to write the next table, which is the application table of SR. So to write application table, we are going to consider the inputs S and R are the normal inputs. Q will be the previous output and Q plus will be the next state output. Since there are three inputs S, R and the previous state, which is Q, right? So we can write total 8 combinations: 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1, right? So for all these 8 combinations, we are going to fill out the last column, that is Q plus, that is next state column. When S and R are 0 0, according to the truth table of SR flip-flop, there is no change in the previous state. If previous state is 0, next state will remain 0. If previous state is 1, next state will remain as 1. Next, when R is equal to 1, the flip-flop is going to, irrespective of the previous state, the next state will be equal to 0 0. If S is equal to 1, irrespective of the previous state, next state will be equal to 1 1, right? And for the last one, we are going to write the don't cares, because the next state is irrespective of the previous state. When S and R both are high, we are going to write the next state values as don't cares, because we are not going to consider that state, right? Next, with this, we are going to write the next table, which is excitation table. For excitation table, Q and Q plus will act as inputs, and S and R will act as output. Since there are two inputs, Q and Q plus, we can write total 4 combinations: 0 0 0 1, 1 0 and 1 1, right? So 0 0 0 0, identify this 0 0, these combinations in application table, right? So 0 0 and Q and Q plus is equal to 0 0 here. So what is the value of S? S is equal to 0, R is equal to don't care, because R is 1 for this combination and R is 1 here. R is 0 here for this combination and R is 1 here for this combination. So R is complement to each other. For that, we will write it as don't care. Next, Q plus 0 1. Q is 0 here, Q is 0 here, and Q plus is 1. Do you have any other combinations apart from this? No, right? So for 0 1, what is the value of S? Is 1. R is equal to 0. For 1 0, Q is 1, Q plus is 1, Q plus is 0, and there is no other combinations apart from only 1. So S is equal to 0, R is equal to 1. Next, for the last one, that is 1 1, I have 1 1 here and 1 1 here, right? So for these two combinations, S is don't care, because S is 0 here and S is 1 and R is 0, right? So this is the excitation table for SR flip-flop, right? So with this excitation table, we are going to write the last table, which we call it as the transition table, right? So I'll rewrite that excitation table of SR. I'll rewrite the excitation table of SR. Q plus S R 0 0 0 1 1 0 1 1. S and R 0 don't care, 1 0 0 1 don't care, 0, right? So with this excitation table we are going to write our last table, which we call it as the transition table. The transition table, for transition table there are two sets of inputs. One is at the previous values Q2 and Q1, because for mode 4 counter we require total 2 flip-flops, so we need to consider two outputs, Q2 and Q1, and next state outputs has Q2 plus and Q1 plus, right? So for Q2, what are the inputs? S2 and R2, and for Q1 inputs are S1 and R1, right? So now there are we are designing mod 4 counter, means there are total 4 states. One is 0 0, next one is 0 1, next one is 1 0 1 1. After 0 0 we will be having the next state as 0 1. After 0 1 we have 1 0. After 1 0 we have 1 1. After 1 1 we have 0 1. Sorry, 0 0. Right? So now fill out these S2, R2, S1 and R1 from the excitation table. Right? So mark the columns which you are going to consider to fill out S2 and R2 values. Okay. So 0 0, S and R is 0, don't care. 0 1 1 0, 1 1 don't care, 0, and the last one 1 0 0 1. And to fill out S1 and R1 we need to check the values of Q1 and Q1 plus. Q1 0 1, so 1 0 1 0 0 1 0 1 1 0, and last one 1 0 0 1, right? So put K-map for S2, R2, S1 and R1. There are two inputs, so two variable K-map we need to put. Inputs are Q2 and Q1, 0 1 0 1. For 0 0 it is 0, for 0 1 it is 1, then don't care 1 0, and it is 1 here, right? So I cannot combine this one with the don't care because they are diagonally present. I cannot make a group of diagonal cells, right? So this one is grouped individually. So what is the expression for S2? For S2 it is Q2 bar Q1, Q2 bar Q1. Next, put K-map for R2. Put K-map for R2. Inputs are again Q2 and Q1. R2 don't care, 0 0 1, right? So again I cannot group this one with this don't care, so we are going to group that one individually, right? So R2 is equal to Q2 Q1, Q2 Q1. Similarly, put K-map for S1. Put K-map for S1. Inputs are Q2 Q1, and fill out those cells 1 0 1 0, right? So what is the expression for S1? S1 is Q1 bar, and the last one R1. For R1, inputs are again Q2 and Q1, 0 1 0 1, and fill out those cells 0 1 0 1, right? Group them. R1 is equal to Q1, right? So these are the expressions for S2 R2, S2 R2. S2 is Q2 bar Q1, R2 is Q2 Q1, and S1 is Q1 bar, R1 is Q1, right? So with these Boolean expressions we are going to design our last or the final circuit of mod 4 counter using SR flip-flop. So as we have already discussed, there are two flip-flops required to design mod 4 counter. The inputs for first flip-flops are S2 and R2. Outputs are Q2 and Q2 bar. And second flip-flop inputs are S1 and R1. Outputs are Q1 and Q1 bar. Right? So as per the Boolean expressions, S2 is equal to Q2 bar and Q1. S2 is equal to Q2 bar and Q1. Okay. R2 is equal to Q2 Q1. R2 is equal to Q2 and Q1. S1, what is S1? S1 is Q1 bar. S1 is Q1 bar and R1 is Q1. R1 is Q1. And these are the two outputs, Q2 and Q1. And we need to connect a common signal to both the flip-flops, which we call it as clock. Okay. So now we will analyze the circuit by assuming the first state as 0 0, right? So when both are 0 0, first we will decide the value of Q1. Since S1 is equal to Q1 bar, Q1 is 0, so S1 is equal to 1, because Q1 is 0 means Q1 bar is equal to 1, which is connected to S1, and R1 is equal to Q1, Q1 is 0, that means S is 1, Q1 will be equal to 1, right? What about Q2? Q2 bar is high, Q1 is 0, output of AND gate is 0, and Q2 and Q1 both are 0, output of this AND gate is also 0. S2 and R2 is equal to 0, that means Q2 is going to remain in its previous state, right? Similarly, next after 0 1, Q1 is 1, which is connected to R, and Q1 bar is connected to S1. That means S1 will become 0 and R1 will become high. That means second flip-flop resets. Q1 is equal to 0. Next, what happens to this first flip-flop? Q2 is equal to previous state of previous value of Q2. You see, Q2 is 0, so Q2 bar will remain 1, and Q1 is 1. 1 and 1, output is 1. And here Q2 is 0. So one input is 0, that means output of this AND gate is 0. Since S2 is high, R2 is 0, Q2 will become 1, right? And for the last case, this will act as a previous value. Q1 is connected to R1. Since Q1 is 0, R1 will become 0, and Q1 bar is connected to S1. Q1 is 0 here, Q1 bar is equal to 1, so S1 is equal to 1. So the second flip-flop sets. What about first flip-flop? Q2 is 0. Q1 is 0. Output of this AND gate will be 0, and Q2, previous state of Q2 was high, so this will become 0. And Q1 is also equal to 0, output of this AND gate is also 0, so both the inputs S2 and R2 are 0. First flip-flop remains in its previous state, which is equal to 1, right? So we got all 4 states. After this state, both the flip-flops should reset, right? See now, Q1 is 1, previous value of Q1 is 1, which is connected to R1. Since R1 is high and Q1 bar is 0, which is connected to S0, R1 is high, S1 is 0, that means the second flip-flop resets. And the first flip-flop here, Q2 is 1, Q1 is also 1, output of this AND gate will be equal to 1, and Q2 bar is 0, output of this AND gate will become 0. Since R1 is high, R2 is high, S2 is 0, Q2 will also reset. So that means we got the previous state, right? So this is the design of a mod 4 counter using SR flip-flop. So in the exam, they may ask design of any type of counter using any type of flip-flop. Okay, so you should be in the position to you should be ready to design any kind of flip-flop, any kind of counter using any kind of flip-flop. Okay, so next we will see the design of mod phi counter, design of mod phi counter using same, that is SR flip-flop. We will see design of mod phi counter using SR flip-flop. First again I will write the excitation table. We will write excitation table first of SR, Q plus S R, 0 0 0 1 1 0 1 1, 0 don't care, 1 0 0 1 don't care, 0, right? So now please don't try to memorize this excitation table, because you will get confused, right? So there are four excitation tables, one for each flip-flop, right? So if you mug up, if you by heart it, and in place of 0 don't care, if you write by mistake, if you write don't care 0, then everything will be wrong, right? So even whatever time you are going to spend, and the ink you are going to spend, as well as the energy, all will go in vain, right? So all will be wasted, right? So excitation table. After that we have the transition table. So we are designing mod phi counter, so we require total 3 flip-flops. We will start from Q3, Q2 and Q1, and Q3 plus, Q2 plus, Q1 plus. Similarly we have 3 sets of inputs, S3 R3, S2 R2 and S1 R1. So there are 5 states starting from 0 0 0, next 0 0 1, 0 1 0, 0 1 1, 1 0 0. Are they 5 states? 1 2 3 4 5, right? Next after 0 0 0, what we will have? The next state as 0 0 1, next 0 1 0. After 2 we have 3, after 3 we have 4, after 4 we have the initial state, that is 0 0 0. Now mark them. Mark, it is good practice of marking these columns, because when you are writing, when you are filling out these columns, S3 R3, S2 R2, S1 R1, you will not get confused, right? So your eyes will see only these marked columns, okay? So 0 0 0 don't care, 0 0 0 don't care, 0 0 0 don't care, 0 1 1 0 1 0 0 1, right? So next next Q2 and Q2 plus, 0 0 0 don't care, then 0 1 1 0, then 1 1 don't care, 0, then 1 0 don't 0 1, 0 0 0 don't care, okay? And the last one Q1 and Q1 plus, 0 1 1 0, 1 0 0 1, 0 1 1 0, 1 0 0 1, and the last one 0 0 0 don't care, okay? So with this transition table, we will put K-map for each of the outputs, S3 R3, S2 R2, S1 and R1, and we will finish out the design, okay? So in this K-map, either this 4 is possible, these 4 cells you can group, right? There are 3 kinds of grouping is possible here, right? And these 4 you can group, these 4 you can group, or these 2 and these 2 you can group, right? So any one expression you can write, and all 3 expressions are correct. Any one if you write, that is correct. So these are the K-maps for S3 R3, S2 R2 and S1 R1, right? So please verify these Boolean expressions. For K-map of R3, K-map for R3, we can write a total 3 expressions, right? So here we can group these 4 elements, right? And this one can be grouped like this, as I did, and these 2 don't cares can be combined with this one and don't care, and you can write 3 different expressions, and you just going to implement only one expression out of those 3, right? And rest all we can only group them only once, right? So this is the final circuit. So please verify these Boolean expressions and verify this circuit. Okay, so this ends up the design of synchronous counter using all flip-flops.